Okay, this is Core Pure 2 Edexcel again, June 2023. It's the last year's paper, and it's question 8. Really bit of an unusual question, this. To do with roots in the complex plane, so on the Argand diagram. But anyway, let's talk it through and see what you've got. So it starts off saying, given that a cubic equation has 3 distinct roots that all lie on the same straight line in the complex plane, describe the possible lines the roots can lie on. Well, if it's a cubic equation, we've got our 3 roots. We've only really got 2 possibilities there that we can look at. We can basically have 3 real roots. Well, 3 real roots on the Argand diagram will basically all lie, therefore, on the real axis. Okay? So that's one scenario where it's going to work, where we have 3 real roots on the, and they all sit in a straight line, and that straight line will have to be, obviously, the x-axis. So, possible line where the roots can all lie, well, that would be y equals 0, is one of the lines. So there's one scenario. The other scenario is if we got 1 real root and 2 complex. And if they're 2 complex, they'll be a conjugate of each other. Now, if they're the conjugate of each other, so, you know, it's like a plus bi and a minus bi, that means they'll be vertically above each other. So the situation where that's going to happen is if we've got our real root there, and then the complex solutions lie directly above and below it, the conjugates of each other, so one being the plus bi and one being the minus bi, but also in the same line there. And that will give us another straight line. Now, what's the equation of that line? Well, it will be x equal whatever, well, in this case it will be x equals a, if I'm calling it a plus bi are ones. So you can just say the other will be if there's 1 real root and 2 complex roots, and that will have an equation of x equals lambda or x equals k or whatever, some value of x. So a vertical line, basically. So describe the possible lines the roots can lie on. The x-axis, or y equals 0, if there are 3 real roots, and x equals some constant where there's 1 real and 2 complex roots are the possible lines where the roots can lie on. Yeah, interesting question to start with. Right, let's move on. So we've got this f of z. I'll just rub this off. I'll have to come back to this in a second. So we've got f of z, which we know is equal to 8z cubed. That 8's going to be important later on. Plus bz squared plus cz plus d. Okay. And it says the roots of fz are distinct and lie on a straight line in the complex plane. Given that one of the roots is 3 over 2 plus 3 over 2i. So if we've got one of the roots being 3 over 2 plus 3 over 2i, remember that situation I've just described. And it's quite a difficult one to do if you haven't fathomed it out from part A. If we've got a complex root, we've got that situation, haven't we? Where the other root is obviously going to be the conjugate of it. So straight away, so we know the other roots are z equal the conjugate of that, so 3 over 2 minus 3 over 2i. And then the other root will be the real root, which will obviously have the same x-coordinate as the complex conjugate pair. So it will have the same x-coordinate, 3 over 2. Or z equals 3 over 2. So those are your 2 other roots. 3 over 2 minus 3 over 2i and 3 over 2 itself. There we go. Okay, I think that was just a 1 marker. So the other 2 roots of fz. Yeah, okay. Right, so now we have another function, g of z, another polynomial, which is, what is it, z cubed plus pz squared plus qz plus 12. And the roots of g of z lie on a different straight line in the complex plane than the roots of fz. So it's not that same line. However, f of z and g of z have one root in common. Well, let's take that to start with. If they got one root in common and it's not this line, g of z, for the roots, then it's got to be this line. It can't be any other vertical line because it's not going to have one root in common, you know. You've either got vertical line for all roots line in a straight line or the x-axis. So if it's going to have one root in common, it's going to have to be the horizontal line going through with that. And we know that has a root of z equals 3 over 2. So that is going to be the root of gz. So if f and z, g of z have one root in common, that root will be that one there. Got to be. Can't be the complex ones because the only other, we can't have another vertical line going through these points, which is different, if you see what I mean. Hope I've explained that. Hope that makes sense. Right, what else did it say? One of the roots of g of z is minus 4. So we know z equals 3 over 2, and we know z equals 4 is one of the other roots. Write down the value of the common root. So that's nice and easy. We've just said that. Z equals 3 over 2 is the common root. And determine the value of the other root of g of z. So we know our roots are 3 over 2. You can see what I'm doing here. I'm writing out the factors basically of g of z. So z minus 3 over 2 is going to be a factor of g of z. Minus 4 is another root, so we know z plus 4 is going to be another factor. And therefore, our other root, let's call it alpha, will be z minus alpha there. That's what g of z is going to be. Now, don't bother expanding it all out and stuff like this. Let's think logically here. Our constant term at the end is 12. And our constant term is these three multiplied together. So minus 3 over 2 times 4 times minus alpha will give us that 12 on the end. So that's going to give us our other root. It's going to give us our 12. So what have we got there? So that's minus 6. So it's 6 alpha, isn't it? 2 minus make a plus. 3 over 2 times 4 is 6. So yeah, 6 alpha equals 12. So alpha is 2. So our other root is 2. So z equals 2 is the other root. Oops, that's very, very poorly done. Right, and lastly, it says, I'm going to come up here if this is okay. Rub this off a little bit. For part D, hence solve the equation f of z equals g of z. Now, we know the roots of f of z, we know the roots of g of z. So why don't we just write them out in this form to start with? So we know g of z, I'll do g of z on this side. We know z minus 3 over 2. It's z plus 4. And it's z minus alpha, which is 2. That's nice. On the other side, our roots of f of z, we've got to be a little bit careful with. We know the roots were, I'm trying to remember now, 3 over 2 plus 3 over 2i, that's it. So it's going to be, let's do the real one first. Z minus 3 over 2. Z minus, let's put this in a bracket, 3 over 2 plus 3 over 2i. Why have I run out of space there? That's stupid of me. Squeeze that in a minute. Let's write it out again. And then z minus the conjugate of that, 3 over 2 minus 3 over 2i. Now, I'll write the g of z. I haven't finished with this yet, so don't worry. I know some of you might be screaming out, hang on a minute, there's something wrong with that. Z minus 3 over 2, z plus 4, and z minus 2. God, I'm running out of room here. That's not very well done, but hopefully that makes sense to you. Now, the thing that doesn't make sense, and hopefully some of you are screaming it out, is look at f of z. It's got an 8 there. So these may be factors, but there will also be an 8 at the front. Otherwise, how on earth are we going to get a z cubed there? 8z cubed there. Be z times z times z. Have to have an 8 there as well. And that's going to make a bit of a difference. However, if we're then trying to solve it to find what z is, z minus 3 over 2, z minus 3 over 2. That's nice. We can just multiply those out. So we're now going to have to multiply out these two, okay, and times it by 8. We're going to get ourselves a quadratic in z, which we're going to be able to solve. So let's deal with this side first of all. 8 on the outside. Obviously, we're going to have z squared. We're going to have these two added together, which are, I'm going mad here, is going to be minus 3, isn't it? Yeah, z times that, and z times that, and the 3 over 2 i's are going to cancel because one's positive and one's negative. So we're going to get minus 3z, and then this times this will give us our final term. So 2 minus make a plus, and then it's going to be 9 over 4 and plus another 9 over 4. So that's going to be 9 over 2, he says. Just make sure I haven't done anything stupid there. 9 over 4, those cancel, and then, yeah, 9 over 4, yeah. So 9 over 2. Right, that's that side done. Over this side, a little bit easier. Z squared, and then we're going to have what? Plus 2z, and we're going to have minus 8. Okay. So, multiplying through here and just solving. 8 squared minus 24z plus 36 equals z squared plus 2z minus 8. Over the other side to make it a quadratic. So you've got 7z squared minus 26z and plus 44 equals 0. Now I've just done all that working out in my head, and most likely I've made an error, but let's just check. I'm going to see if that's what I got earlier, but be a second. 7z squared minus 26z plus 44. Oh, didn't make a mistake. Yeah. So, stick that into your quadratic solver, and you get actually two complex answers. And again, I'm just going to cheat here and just write down what I got earlier. So, it's 13 plus or minus I root 79, he says. Oh no, 139 even. Can't read me right. Over 7, I do believe. Yeah. So that is our solution. Now then, there is one other solution though, and that's, you've got to remember, we cancelled out z minus 3 over 2, didn't we? You know, right at the beginning when we cancelled out the z minus 3 over 2. So therefore, 3 over 2 is also a solution. And don't, you know, this is cubic equations, aren't they? So we're going to expect 3 answers. So we've got our 2 complex answers. Don't forget the 3 over 2, because when we cancelled out those 3 over 2s there, lovely, to make our life a little bit easier, we are therefore losing z equals 3 over 2 as a solution. So just be on your toes about that. It's easy to forget the 3 over 2. There we go. Hope that makes sense.